Energy and energy changes. Energy is the capacity to do work or transfer heat. All forms of energy are either kinetic or potential. Kinetic energy, E subscript K, is the energy of motion. The formula for kinetic energy is energy equals half times the mass of the object times the velocity squared. One form of kinetic energy of particular interest to chemists is thermal energy, which is the energy associated with the random motion of atoms and molecules. Potential energy is the energy possessed by an object by virtue of its position. There are two forms of potential energy of great interest to chemists. Chemical energy is the energy stored within the structural units of chemical substances, and the electrostatic energy is a potential energy that results from the interaction of charged particles. The formula for this is electrostatic energy is proportional to the charge of one particle times the charge of the second particle divided by the distance between the two particles. Kinetic and potential energy are interconvertible. One can be converted to the other. Think about it in terms of a skateboarder in a half pipe. As the skateboarder stands at the top of the half pipe, he has an awful lot of potential energy, but because he is not moving, he has no kinetic energy. As he goes into the half pipe and starts moving, he now has an awful lot of kinetic energy and is using up any potential energy. Once he reaches the top of the other side of the half pipe, once again he stops in motion, he floats in the air, and at that point he has all the potential energy he can have, whilst no kinetic energy because he is not moving, and so on and so forth. Although energy can assume many forms, the total energy of the universe is constant. Therefore, energy can neither be created nor destroyed. When energy of one form disappears, the same amount of energy reappears in another form or forms. This is known as the law of conservation of energy. The SI unit of energy is the joule, big J, named after the English physicist James Joule. It is the amount of energy possessed by a 2 kilogram mass moving at a speed of 1 meter per second. If we put those values into the equation for kinetic energy, we will see that half times 2 kilograms times 1 meter per second equals 1 kilogram per meter squared per second squared, which is equal to 1 joule. The joule can also be defined as the amount of energy exerted when a force of 1 Newton is applied over a distance of 1 meter. Because the magnitude of joule is so small, we often express larger amounts of energy using the units kilojoule, where 1 kilojoule is 1,000 joules. The nature of light. Visible light is only a small component of the continuum of radiant energy known as the electromagnetic spectrum. Here, for example, all the way to the left, we see gamma rays, the rays that created the Hulk. As we get a little longer in wavelength, we have X-rays, we have ultraviolet light, then we get to visible light, which is all the colors we see. Past that, we have infrared lights, so heat lamps, for example. Keep on going, we get microwaves, and those range from our microwave ovens to cell phones. And finally, past that, we reach radio waves. Of course, we can only see colored light or white light. We cannot see radio waves, microwaves, or X-rays, but they are all part of the same electromagnetic spectrum. The speed of light, c, through a vacuum is a constant. c equals 2.9979248 times 10 to the 8 meters per second, although normally it's rounded to 3 times 10 to the 8 meters per second. The speed of light, frequency, and wavelength are related in the following equation, where c, the speed of light, is equal to lambda, the wavelength in meters, times frequency, shown by the funky V letter, also known as nu in the Greek alphabet, with the units of reciprocal seconds, so per second. This is also known as a hertz. So if you hear hertz or per seconds, same thing. This is a very nifty equation as we can convert between the speed of light, wavelengths, and frequencies. So in other words, if we know a wavelength, we can calculate the frequency as speed of light is constant. All forms of electromagnetic radiation travel in waves. Waves can be characterized by their wavelength, which is the distance between identical points on successive waves. So we don't necessarily have to be counting it from the peaks of the wave. We can also calculate them from the troughs as long as it's a repeating unit that is equal. The wavelength will be the distance between the exact same points on two repeating units. The frequency is the number of waves that pass through a particular point in 1 second. So the more waves that pass through that unit per unit time, the higher the frequency. And then amplitude is the vertical distance from the midline of a wave to the top of the peak or the bottom of the trough. So in other words, the larger the wave in the y-axis, the higher the amplitude. The electromagnetic spectrum. The electromagnetic wave has both an electric field component and a magnetic component. They are both orthogonal to each other. The electric and magnetic components have the same frequency and the same wavelength. The double-slit experiment. When light passes through two closely spaced slits, an interference pattern is produced. So, what the hell does that mean? It means that when we shine light through a slit, in this case S0 on the first screen, that light will then shine through onto a second screen with two slits next to each other, S1 and S2. As the light passes through these two slits, we notice that the light shown at the end onto the wall is actually in this pattern shown in figure B. So you have bright sections and dark sections. This should confuse you, because we only had two slits. Why do we now have multiple lines varying in brightness? How is this possible? Well, the light must be interfering with each other. Constructive interference is a result of adding waves that are in phase. Think of it as two ripples on a pond coming together at the same time, so you get a much bigger ripple at that point. That would be the bright light. That would be constructive interference. Whilst destructive interference is a result of adding waves that are out of phase. So this would be when two ripples that are opposite to each other hit each other on the pond and they cancel each other out. Well, the same happens with light. We end up with these dark spaces where no light appears to come through because the light cancels itself out. The fact that we observe these interferences, typical of waves, demonstrates the wave nature of light. Quantum theory. Early attempts by 19th century physicists to figure out the structure of an atom met with only limited success. They were using the laws of classical physics, and these laws describe the behavior of macroscopic objects. Over time, the realization and acceptance was that the behavior of subatomic particles is not governed by the same physical laws as larger objects. So in other words, what happens on a large scale does not necessarily happen on a small scale. Quantization of energy. When a solid is heated, it emits electromagnetic radiation, known as black body radiation, over a wide range of wavelengths. The amount of energy given off at a certain temperature depends on the wavelength. Classical physics assumes that radiant energy was continuous, that is, could be emitted or absorbed in any amount. Max Planck suggested that radiant energy is only emitted or absorbed in discrete quantities like small packages or bundles. A quantum of energy is the smallest quantity of energy that can be emitted or absorbed. The energy of a single quantum of energy is E equals h nu, where h is called Planck's constant and is equal to 6.63 times 10 to the negative 34 joules per second, mu of course being the frequency of a wave, and energy, well, is the energy. The idea that energy is quantized rather than continuous is like walking up a staircase or playing the piano. You cannot step or play anywhere continuous. You can only step on a stair or play on a key, which is quantized. Photons and the photoelectric effect. Albert Einstein used Planck's theory to explain the photoelectric effect. The apparatus for this experiment is shown on the right. So the idea is that you shine some light on a metal and you have a rod connected to a voltage source, and you will be able to see flow of electricity even though the rod and the metal are not connected, which is highly unusual. This implies that electrons must be moving through the air, and the only thing that could be giving it that energy to jump through the air is the light being shown on it. Let's elaborate on this. Electrons are ejected from the surface of metal exposed to light of a certain minimum frequency, called the threshold frequency. The number of electrons ejected is proportional to the intensity or brightness of the light. However, below the threshold frequency, no electrons were ejected, no matter how intense the light. Einstein proposed that the beam of light is really a stream of particles. These particles of light are now called photons. Each photon must possess the energy given by the equation. The energy of a photon is equal to Planck's constant times the frequency of the light. Shining light onto a metal surface can be thought of as shooting a beam of particles, photons, at the metal atoms. If the frequency of the photons equals the energy that binds the electrons in the metal, then the light will have enough energy to knock the electrons loose. As the equation for the energy of a photon suggests, the frequency is proportional to the energy, therefore high frequency is proportional to high energy. If we use light of a higher frequency, then not only will we see the electrons get knocked loose, but they will also acquire some kinetic energy. This is summarized by the equation that the energy of a photon is equal to the kinetic energy plus the binding energy of the electron. If the energy of the photon is not high enough to overcome the binding energy, then nothing happens. When the energy of the photon is equal to the binding energy, the kinetic energy is still equal to 0, but that would imply that Planck's constant times the frequency of the light is equal to W, the binding energy of the electron. If the energy is higher than the binding energy of the electron, then we will see values for the kinetic energy of the ejected electron. Long story short, what this tells us is that if we know the binding energy of the electron to the metal, then we can figure out what the minimum frequency required for light is to eject these electrons. Or if we want to know what the binding energy of the electron to the metal is, all we have to do is the photoelectric experiment and find the minimum frequency of light that causes electrons to be ejected. Pretty useful. Anyway, moving on. Bohr's theory of the hydrogen atom. Sunlight is composed of various color components that can be recombined to produce white light. The emission spectrum of a substance can be seen by energizing a sample of material with some form of energy. The red hot or white hot glow of an iron bar removed from a fire is the visible portion of its emission spectrum. The emission spectrum of both sunlight and a heated solid are continuous. All wavelengths of visible light are present. Line spectra are the emission of light only at specific wavelengths. So if we run high voltage through a vacuumed sample of an element such as hydrogen, and the light given off that is shown onto a panel with a slit, and the light coming out of the slit is hit with a prism, instead of seeing a rainbow, we will only see specific lines at specific wavelengths. Every element has its own unique emission spectrum. Here in this image, we see some images of multiple different elements and their bright line spectra. Consider it an atomic fingerprint. This is what is used if we're trying to figure out what elements are present on planets far, far away. We can collect the light coming from those specific planets and study the emission spectrum, and therefore derive what elements are present from wherever that light is coming from. The Rydberg equation can be used to calculate the wavelengths of the 4 visible lines in the emission spectrum of hydrogen. So 1 over the wavelength of the spectrum line is equal to the Rydberg constant, which is equal to 1.097373317 times 10 to the 7 reciprocal meters, times, in parentheses, 1 over n1 squared minus 1 over n2 squared, close parentheses, where n's are positive integers and n2 must always be bigger than n1. Niels Bohr attributed the emission of radiation by an energized hydrogen atom to the electron dropping from a higher energy orbit to a lower one. As the electron dropped, it gave up a quantum of energy in the form of light. Bohr showed that the energies of the electrons in a hydrogen atom are given by the equation energy of the orbit is equal to negative 2.18 times 10 to the negative 18 joules times 1 over n squared, where n is the positive integer. As an electron gets closer to the nucleus, n decreases. Therefore, the energy n becomes larger in absolute value, but more negative as n gets smaller. The energy is most negative when n equals 1. We would call this the ground state, the lowest energy state of the atom. For hydrogen, this is the most stable state. The stability of the electrons decreases as n increases. Therefore, each energy state in which n is bigger than 1 is called an excited state. Bohr's theory explains the line spectrum of the hydrogen atom. Radiant energy absorbed by the atom causes the electron to move from the ground state to an excited state. Conversely, radiant energy is emitted when the electrons move from the higher energy state to a lower energy excited state, or the ground state. The quantized movement of the electrons from one energy state to another is analogous to a ball moving down steps. When a ball moves between shallow steps, there's only a small difference, whilst as it gets to a bigger step, it drops down further, until it hits the ground, where it is most stable, with the lowest potential energy. Using the notation that Ni is the initial state and Nf is the final state, a photon is emitted when the N initial state is bigger than the N final state. Therefore, the change in energy is negative as energy is lost to the surroundings in the form of a photon. A photon is absorbed when Nf is bigger than Ni. Therefore, the change in energy is positive as it gained the energy of the photon. The energy difference between the initial and final states is change in energy is equal to the Planck's constant times frequency, which is equal to negative 2.18 times 10 to the negative 18 joules, times, parentheses, 1 over the final state squared minus 1 over the initial state squared. This equation becomes more useful if we're trying to figure out what the wavelength of the light being emitted is. To calculate the wavelength, we do need to recall that the speed of light is equal to wavelength times frequency. So if we want to substitute the frequency in this equation, we can do so by substituting any frequency mentioned by the speed of light over the wavelength. We substitute those values into the equation to give us 1 over the wavelength, lambda equals 2.18 times 10 to the negative 18 joules over Planck's constant times the speed of light, times our parentheses 1 over the final state squared minus 1 over initial state squared. So, long story short, we can associate each line on hydrogen emission spectrum to the movement of an electron from a higher energy shell or high energy state to a lower energy state. So from these shells or orbitals that the electrons are located in. So for example, the blue line is from the n equals 4 state, or the fourth orbital, dropping down to the second orbital. The red line is from the electron in the third orbital dropping down to the second orbital, and so on and so forth. All of these observed wavelengths can be matched to a transition of an electron from a high orbital to a lower orbital using the change in energy equation. These changes in electron state from higher shells to lower shells can be separated into multiple series pretty much by where the electron ends at the end of the transition. We can also put them in different spectrums because that's where the light given off is found. So whenever an electron drops to n equals 1, or the lowest energy ground state orbital, we would refer to these transitions as the Lyman series. We cannot see it or observe it because it is an ultraviolet emission. However, the Balmer series, when n equals 2, the second highest electron orbital, we can see it because those transfers or transitions are in the visible spectrum. The n equals 3 and n equals 4 series are called the Paschen and the Brackett series. But once again, these are in the infrared region and we cannot observe them visually. Wave properties of matter. Louis de Broglie reasoned that if light can behave like a stream of particles, photons as we know them, then electrons could exhibit wave-like properties. According to de Broglie, electrons behave like standing waves, i.e. waves that are limited in their space to work with. Think of a guitar string. It is of a certain length, and when you strum it, it forms different waves. But the distance is always set to a limit. Only certain wavelengths are allowed. If you get multiple waves within this set distance, you will form nodes. At a node, the amplitude of the wave is 0. So what does this have to do with the electrons? Well, if you think about it, an electron orbiting a nucleus has somewhat of a circumference to be in, and that circumference is a set distance. Therefore, if it were to be a wave, it would only be able to have set wavelengths because you have a limited distance. De Broglie deduced that the particle and wave properties are related by the following expression. Wavelength associated with the particle equals Planck's constant divided by the mass of the particle in kilograms times the velocity in meters per second. The wavelength calculated from this equation is known as the de Broglie wavelength. And due to its generic nature, it implies that we can calculate the wavelength of practically any object with a mass and velocity. We can calculate, say, the wavelength of a bee flying in the air, or the wavelength of a bus driving down the highway. But more usefully, we can calculate the wavelength of an electron at a certain speed. Diffraction of electrons. Experiments have shown that electrons do indeed possess wave-like properties. For example, if you take the X-ray diffraction pattern of aluminum foil, and you take aluminum foil and shine X-rays on it, this is what you observe. These rings on the left show interference patterns of waves that are then shown on our detector plates. Remember that interference can only happen with waves. Well, if we do the same experiment with electron rays, we get a very similar pattern from aluminum foil, implying that there's also wave-like interference, and therefore electrons, as that's what we're shining on it, should probably be wave-like. Long story short, we can now say that electrons are both particles and waves. Quantum mechanics, the uncertainty principle. The Heisenberg uncertainty principle states that it is impossible to know simultaneously both the momentum, p, and the position, x, of a particle with certainty. The equation looks something like this. The change in position times the change in momentum is bigger than or equal to Planck's constant over 4 times pi, where change in position is the uncertainty in position in meters, and change in momentum is the uncertainty in momentum. As momentum is mass times velocity, we can change the equation slightly to give us the uncertainty in position times mass times uncertainty in velocity is bigger than or equal to Planck's constant over 4 pi. The Schrödinger equation and the quantum mechanical description of the hydrogen atom. Erwin Schrödinger derived a complex mathematical formula to incorporate the wave and particle characteristics of electrons. Wave behavior is described with the wave function psi, also known as the devil's pitchfork. The probability of finding an electron in a certain area of space is proportional to psi squared and is called the electron density. Quantum mechanics defines the region where the electron is most likely to be at a given time. So to unravel this, what we're saying is, instead of the electrons being in very neat orbitals or orbits flying around the nucleus, we now have a less defined area with high probability of where the electron is going to be found. And the electron could be anywhere in this area. The higher the electron density, the more likely the electron is located there at any given time. The Schrödinger equation specifies possible energy states an electron can occupy in a hydrogen atom. The energy states and wave functions are characterized by a set of quantum numbers. Instead of referring to orbits as in the Bohr model, quantum numbers and wave function describe atomic orbitals. Quantum numbers. Quantum numbers are required to describe the distribution of electron density in an atom. There are 3 quantum numbers necessary to describe an atomic orbital. The principal quantum number, n, which designates the size of the orbital. The angular momentum quantum number, L, which describes the shape. And the magnetic quantum number, ml, which specifies the orientation of said atomic orbital. The principal quantum number n designates the size of the orbital. Larger values of n correspond to larger orbitals. The allowed values of n are integral numbers, 1, 2, 3, and so forth. The value of n corresponds to the value of n in Bohr's model of the hydrogen atom, i.e., as n got bigger, you got to a bigger orbit. Well, now we're talking about bigger atomic orbital. A collection of orbitals with the same value of n is frequently called a shell. The angular momentum quantum number L describes the shape of the orbital. The value of L are integers that depend on the value of the principal quantum number. The allowed values of L range from 0 to n minus 1. For example, if n equals 2, L can be 0 or 1. L, when equals 0, is an s orbital. When it equals 1, it's a p orbital. When it equals 2, it's a d orbital. And when it's 3, it's an f orbital. So, long story short, you're probably going to see different shaped orbitals, and they will be designated s, p, d, and f. Just know that that comes from the angular momentum quantum number. A collection of orbitals with the same value of n and L is referred to as a subshell. The magnetic quantum number, ml, describes the orientation of the orbital in space. Think of it as the x, y, and z axes in space. The value of ml are integers that depend on the value of the angular momentum quantum number. That's a bit of a mouthful, so just let's look at the table at the bottom here. You will notice that when n equals 2, for example, L can either be 0 or 1, and when L is 0, the ml can only be 0, implying that there are no x, y, or z axes. Your orbital is probably symmetrical. Whilst when L equals 1, you have an ml value of -1, 0, or +1. these correspond to the three axes, x, y, and z. So it's telling us that when L equals 1, we have 3 orbitals. Do you really have to worry about this? No, not really. We do not have to worry about these numbers per se. We can just look at the actual orbitals. The quantum numbers designate shells, subshells, and orbitals. So in this picture here, each box is an orbital. Each shell is just the different orbitals at that subshell. And each shell is defined by n. So we look at it vertically, which groups are together. For example, this is a shell, this is a shell, this is a shell. And these shells are where your electrons go. There's one final quantum number, which is the electron spin quantum number, which is used to specify an electron's spin. There are two possible directions of spin. They're either up or down. The allowed values of ms are +½ or -½ This can be shown experimentally as a beam of atoms can be split by a magnetic field, and statistically half the electrons spin clockwise and the other half spin counterclockwise. To summarize quantum numbers, the principal quantum number n is for the size, the angular quantum number L is for the shape, and the magnetic quantum number ml is for the orientation. All three are required to describe an atomic orbital. So for example, an atomic orbital 2px, shown on the right, 2 is the principal quantum number, p is the angular momentum, where L equaled 1, and x is related to the magnetic quantum number, telling us which axes it is in. i.e., if we look at the XYZ axis, we see that this dumbbell shape is along the x-axis. And then we have the electron spin quantum number, which is the direction of the spin, which is required to describe the electron in an atomic orbital. Now, if you are really confused, then take a moment, look at this slide, and just know that we can get by with just knowing the principal quantum number, and we can memorize the S, P, D, and F, i.e. the angular momentums, by looking at the periodic table. Atomic orbitals. All s orbitals are spherical in shape but differ in size, where 1s is smaller than 2s, which is smaller than 3s, which makes sense because if you think about what that number is, that is the principal quantum number implying size. As the number gets bigger, the orbital gets bigger. The p orbitals are pretty much split into two regions, sometimes shown as a dumbbell, where you cannot have electrons in the middle because that was where the nucleus is located, i.e. where all the axes meet. There are three possible orientations to a p orbital, one in the x-axis, one in the y-axis, and one in the z-axis. The d orbitals are somewhat like the p orbitals, but with a little cherry on top, and there are 5 of them. Do not have to worry about them too much. Energies of orbitals. The energies of orbitals in the hydrogen atom depend only on the principal quantum number. So when n equals 1, we have one energy level. When n equals 2, we have a second energy level, and so on and so forth. The example here is that the first shell only has one s orbital. The second shell has both the 2s and the 2p's. The 2s subshell is your s orbital at that energy level, and the 2p subshell is your p orbitals at that energy level. And there are 3 p orbitals because they are in the 3 different axes. The third shell, high up in energy, where n equals 3, you have the 3s, the 3 3p's, and the 5 3d's. The 3s subshell, which is bigger than your 1 and 2s's. You still have the 3p subshells, which once again, they are the x, y, and z axes, higher energy than your 2p orbitals. And then we have the 5 3d orbitals making up your 3d subshell. Electron configuration. The electron configuration describes how the electrons are distributed in the various atomic orbitals. In a ground state hydrogen atom, the electron is found in the 1s orbital. So in other words, the electron, shown as an arrow in the 1s box in the bottom left, remember it has a spin, so we're showing that it has spin in one direction, is found in the lowest energy orbital. We refer to this as the ground state electron configuration of hydrogen. The way we would write it is capital 1 for the energy level, S, the shape of the orbital, and then superscript 1 indicating the number of electrons in the orbital or subshell. If hydrogen's electron is found in a high energy orbital, the atom is in an excited state. So a possible excited state could be if that electron jumped up into the 2s orbital, and therefore we end up with a 2s superscript 1 configuration. So let's take a moment to look at the emission spectrum again. Remember that hydrogen had 4 visible bands. This was the Balmer series, and these were electrons dropping down from a high energy state to a low energy state, right? Well, they were going from one energy level to another, so clearly with hydrogen we have 4 energy levels. The bottom one here is helium, and we can see that it has multiple bands. The helium emission spectrum is more complex than the hydrogen spectrum. There are more possible energy transitions in the helium atom because the helium has 2 electrons. In a multi-electron atom, the energies of the atomic orbitals are split. The splitting of energy levels refers to the splitting of a shell into subshells of different energies. So in other words, even though your quantum number remains the same, your 1, 2, 3, 4, and 5, the s orbital is at a different energy than your p orbital. Your d orbital is different to your s and your p, and so on and so forth. You may even notice that the 4s is at a lower energy than your 3d orbitals. Interesting stuff. According to the Pauli exclusion principle, no 2 electrons in an atom can have the same 4 quantum numbers. That means that if we want to put electrons into a 1s orbital, it can fit 2 electrons in there. As they cannot have the same quantum numbers, it means that the one that needs to vary is the least significant one, which is the electron spin one, which means that when we put electrons into an orbital, they must have opposite spins. This also explains why we can't put in more than 2 electrons, because we only have 2 options. We have an up spin or a down spin. If we try to put a third electron in there, it would have to match one of the other 2. Otherwise, we would not be able to differentiate between the 2. This is why when we have helium with 2 electrons, we would write the electron configuration for helium as 1s2, quantum number 1, shape S, 2 electrons. We can see to the left that we have an arrow pointing up and an arrow pointing down, indicating the spins of the 2 electrons. The Aufbau Principle states that electrons are added to the lowest energy orbitals first before moving to higher energy orbitals. So lithium, for example, has a total of 3 electrons. So it means that the first 2 electrons would go into the 1s orbital, one pointing up, one pointing down, and the third electron must go into the next available orbital with the lowest possible energy, which would be the 2s orbital. The ground state electron configuration for lithium would be 1s2, 2s1. For beryllium, which has a total of 4 electrons, the ground state electron configuration would be 1s2, 2s2, and our 2 electrons must have opposite spins in the 2s orbital also, just like in the 1s. Once we move on to boron, which has 5 electrons, we are now having to put an electron into the 2p orbitals. The ground state electron configuration of boron would be 1s2, 2s2, 2p1. According to Hund's rule, the most stable arrangement of electrons is the one in which the number of electrons with the same spin is maximized. Therefore, carbon, with a total of 6 electrons, would have 2 electrons in the 2p orbital, so its electron ground state configuration would be 1s2, 2s2, 2p2, but we would not pair the electrons into a single orbital. Instead, we would put them in 2 separate orbitals with the same spin. This is Hund's rule in action. Another term that is often used when talking about these things is that when you have orbitals of equal energy, such as the 2p orbitals, we would say they are degenerate. Nitrogen has a total of 7 electrons, so the ground state electron configuration of nitrogen is 1s2, 2s2, 2p3. Once again, we put that third electron into the third empty orbital to give us 3 orbitals with electrons with equal spin, following Hund's rule. Once we reach oxygen, oxygen has 8 electrons, the ground state being 1s2, 2s2, 2p4. At this point, we have run out of empty degenerate orbitals, so we have to start pairing the electrons. Well, at this point, we go back to the usual, putting an electron into the same orbital as another, but make sure to invert your spin. So one is up, the other is down. Fluorine has a total of 9 electrons, with a ground state electron configuration of 1s2, 2s2, 2p5. And here we see we have 2 electron pairs and 1 single electron in our 2p orbitals. When there are 1 or more unpaired electrons, as in the case of oxygen and fluorine, the atom is called paramagnetic. Neon has a total of 10 electrons, so its ground state electron configuration of 1s2, 2s2, 2p6 has completely full orbitals. When all of the electrons in an atom are paired, as in neon, it is called diamagnetic. So, long story short, the general rules for writing electron configurations is 1. Electrons will reside in the available orbitals of the lowest possible energy. Each orbital can accommodate a maximum of 2 electrons. Electrons will not pair in degenerate orbitals if an empty orbital is available, and orbitals will fill in the order indicated in the figure to the right. Notice that things start getting weird once we start putting electrons past the 3p orbital. We fill the 4s before we fill the 3d. We go back to 4p and then we fill the 5s before we go to 4d. We fill the 5p and the 6s before we even get to the 4f, and so on and so forth. Electron configuration in the periodic table. As there are so many elements in the periodic table, this could become extremely tedious to write all the electron configurations of every element. The electron configuration of all elements except hydrogen and helium can be represented using a noble gas core. So for example, the electron configuration of potassium with 19 electrons is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Because 1s2, 2s2, 2p6, 3s2, 3p6 is the electron configuration of argon, we can simplify potassiums to argon 4s1, because argon will always be the same. Elements in group 3b through 1b are the transition metals, shown in the red box here. Following lanthanum La, there is a gap where the lanthanide rare earth series begins, and after actinium comes the actinide series. If we include the lanthanides and actinides into the periodic table, we will see the bigger picture of how the periodic table is arranged. And voila, here we can see that the periodic table is arranged literally by their electron configurations, and more specifically by the shapes of the orbitals. We have the S block to the left, the F block, the D block, and then the P block. So in other words, the furthest out electron for each element defines where the element is located in the periodic table. So for example, carbon having a outermost electron in the p orbitals, specifically in the 2p orbital, we find it in the p block. All transition metals are going to have their electrons in the d block, and these actinides and lanthanides that we just heard of would be located in the f block. There are several notable exceptions to the order of electron filling for some of the transition metals. For example, chromium with 24 electrons is argon 4s1 3d5 and not argon 4s2 3d4 as expected. Copper with 29 electrons is argon 4s1 3d10 and not argon 4s2 3d9 as expected. The reason for these anomalies is the slightly greater stability of d subshells that are either half filled, d5 in the case of chromium, shown here with a single electron in each orbital, or completely filled, d10, such as shown here with copper, where we only have one electron in the 4s and completely filled 3d subshell.